What Frank Herbert describes in his pages of Dune, the Coriolis storms of Arrakis, is grounded in real atmospheric science. And when you understand the actual meteorology behind it, they become something even more terrifying than what the novels let on. Today we're going to go deep. We're going to break down exactly what a Coriolis storm is, what it creates, and what it does to everything in its path. And then, at the end of the video, I'm going to show you something that might genuinely surprise you, where the storm exists already, right now, in our own solar system. Arrakis teaches the attitude of the knife, chopping off what's incomplete and saying, now, it's complete because it's ended here. Before we talk about the storm, we need to talk about the world that builds it. Arrakis is a desert planet, but that description barely even touches on the surface of what it really means. It's not a desert in the way that the Sahara is a desert, where you've got, dry land interrupted by oases and river systems and coastlines on the edges, and it has atmospheric moisture above it moving in from the oceans around it. Arrakis has none of that. There's no open water, there's no polar ice caps of any kind, and there's really no moisture buffer around it. And to use a meteorological term, it is a planet-wide heat engine with nothing to regulate it. Think about what moisture does in Earth's atmosphere. Water vapor is essentially like a shock absorber for heat. When the air warms up over land and rises, the moisture in the atmosphere condenses, it releases latent heat, and that process helps moderate these temperature swings and organize where and how energy is distributed. So if you remove that moisture, suddenly you have nothing standing between surface heating and pretty much catastrophic convective instability. On Arrakis, the surface temperature in the open erg, like the open desert there, can reach 70 to 80 degrees Celsius. That's 160 to 175 degrees Fahrenheit. While up in the upper atmosphere, it's going to remain brutally cold. That temperature differential, or the gap between the superheated surface and the cold air aloft, is the engine that really drives everything. In real-world meteorology, we measure atmospheric instability using a value called CAPE. That's convective available potential energy. It tells you how much energy is available for a rising air particle to keep going up. On Earth, a severe thunderstorm, you can see CAPE values of 3,000, maybe up to 4,000 joules per kilogram. On Arrakis, the equivalent value with, what Frank Herbert describes about the surface heat and the total absence of moisture would likely be, tens, if not tens of thousands of joules per kilogram. So here's where it starts to get really interesting, because Earth already has a real-world comparison sitting right in the middle of the Sahara Desert and some other large deserts in the world, and that's called the Haboob. Now, it's a kind of a funny name, but a Haboob is a wall of dust and sand that's generated primarily from the outflow of a collapsing thunderstorm. If you've seen some other weather explainer videos, think of a downburst from a thunderstorm with those really intense, fast winds picking up dust and starting to push it at incredible speeds. Now, these can roll across Sudan, Egypt, the American Southwest, and some of the largest haboobs can reach up to 1,500 meters in height, and they move around 60 to 100 kilometers an hour. That's not how fast the wind speeds are, because the wind speeds can reach, up to 200 kilometers an hour. But, they're pretty scary to see just pop up some random day. And, talking about day, these haboobs turn day into night. So, take the haboob and remove all the moisture that's limiting its development, and remove the storm that created it too, and replace that trigger with a planet-scale pressure system. Give it thousands of kilometers of open desert to accelerate across with nothing to slow it down, and then multiply the available energy by a factor of 10. And that's going to be your Coriolis storm. The mystery of life isn't a problem to solve, but a reality to experience. Every major weather event has ingredients. A tornado needs instability, it's got to need wind shear, lift, and moisture. A hurricane needs warm, open water over an ocean, some low-level wind shear, an upper-level exhaust, and a pre-existing disturbance. Coriolis storm on its own has its own specific recipe. And when you map it against real atmospheric science, it all checks out, scientifically. So the first ingredient is going to be thermal instability. We've already kind of touched on this. On the surface of Arrakis, it gets really hot, and the upper atmosphere is cold. So the vertical temperature differential means that any particle near the surface is very, very buoyant and wants to shoot straight up and really fast. And in a moist atmosphere, that energy gets partially spent in condensation and precipitation. But on Arrakis, there's no release. So all that energy goes directly into vertical wind velocity. So updrafts would be measured in, I don't even know how you would measure it. It wouldn't be meters per second. It would be, tens of meters, decameters, whatever you want to call it. But it would be very fast. Next one's going to be wind shear and the Coriolis effect. And this is where, the name of the storm comes in effect. The Coriolis effect is real. It's the deflection of moving air, which is based off of the planet's rotation. So on Earth, it's why hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern. And on Arrakis, Herbert specifically names these storms after the effect, which is implying that, the planet scale rotation is a key organizing force of how they develop and steer. Now, wind shear, which is the change in wind speed and direction with height, is what allows the storms to organize and persist rather than just, explode upwards and then collapse. On Earth, wind shear is what turns a garden variety thunderstorm into a huge supercell. On Arrakis, with a planet-scale pressure system driving the flow, and nothing to disrupt the shear profile over, thousands of kilometers, these storms can achieve organized rotation on a scale that has no Earth equivalent. So, onto the third part, and it's where Arrakis storms get a feature that Earth storms really don't have at the same scale, and it's the sand itself kind of becomes part of the storm's engine. On Earth, the dust and sand suspended in an atmosphere actually has a complex effect on the storm. Fine particles absorb solar radiation and they heat the air around them. It can actually start enhancing the convective instability, like feeding the storm that's carrying them because of the heat. So on a planet where the surface is entirely sand, this feedback loop becomes the defining feature of how the storm kind of sustains itself. The storm picks up sand, the sand heats the air, the heated air intensifies the wind that picks up the sand, and it just goes on and on and on as a self-reinforcing cycle. So there's another weird kind of part to this too, and it's real, it's documented, it's a little weird, and it's called triboelectric charging. And that happens whenever particles collide and transfer electrons. In a sandstorm, billions of sand and dust particles collide continuously as they're, carried in the air. And the result is this massive buildup of electrostatic charge. It's the same basic process that creates lightning, but it's distributed throughout the entire storm system rather than concentrated in a single cloud or a couple clouds. So real-world haboobs and dust storms routinely generate enough electrostatic fields to, damage electronics. They can disable vehicles and even produce visible lightning, lightning-like or pseudo-lightning discharges within the dust cloud itself. So in a storm, a Coriolis storm with Arrakis' particle density and vertical scale, you're not talking about, like occasional sparks. You're talking about a storm that is simultaneously colossal. It's also an electric event, and it has these flickering lights at the edges that our Fremen scout is seeing. Now, why does Frank Herbert say that they're around 800 meters and they move around 300 kilometers an hour, or they have winds up to 700, 800 kilometers an hour inside the storm? So on Earth, our largest haboobs reach around 1,500 meters up into the atmosphere, and they're driven just by the outflow of a strong thunderstorm. It has all these other things that are kind of weakening it. You have moisture in the atmosphere, you have terrain and everything that's kind of lowering the speed of wind. But on a planetary scale, moisture-free, friction, minimal system that's driving sand across in pretty much an unbroken desert, the vertical extent and forward speed that Frank Herbert are describing are kind of an under-exaggeration. I mean, it would be reasonable to be giving numbers, triple, quadruple what is happening on Earth. Deep in the human unconscious is a pervasive need for a logical universe that makes sense. But the real universe is always one step beyond logic. Let's go back to that siege. You got the wall on the horizon. The naive has given the word, and now we're going to walk through what actually happens, stage by stage, using real atmospheric science and, what the Fremen are probably going to be doing during this time. So, stage 1. This is long before the wall of sand arrives. The storm is going to be announcing itself through a pressure change. The massive low pressure of the storm's core is drawing in surrounding air, causing an inflow wind that feels almost gentle at first. It's going to be warm, dry, it's going to be kind of gritty with all the sand kind of pushing through. And on Earth, experienced desert travelers can probably detect this happening, either from, oh, my knee is hurting, there's going to be rain coming in soon, or they might start tasting something a little bit metallic because there are these fine metallic particles in sand. This happens on Earth too, but in Frank Herbert's books, the Fremen call this the breath of Shai-Hulud. Meteorologically, this is the inflow boundary, and it tells you pretty much exactly how much time you have left. So barometric pressure is going to drop measurably in the next hour or so before the major storm, and the Fremen siege architecture, which is going to be built into rock faces and cave systems, is essentially a passive barometric instrument. The way air is going to be moving through the tunnels changes as the pressure drops, and might have some kind of sound effects, maybe something kind of humming, like a low drum or like a low hum as this air is pushing through the siege. So next thing that's going to happen is going to be, your hair on your arm, the back of your neck is going to start rising. You're going to have metal objects that feel warm to the touch, and if you have any exposed electronics, they're going to start failing. That's the triboelectric charging reaching the leading edge ahead of the sand wall itself. So these are fine particles too small to see, carrying the storm's electrical signature kilometers ahead of the visible front. In the siege, this is a signal to really start locking up anything conductive. Your sandworm thumpers, things like your maker hooks, any kind of metal things there, even like the still suit. If you have any kind of electronics that make it work, you want to make sure that it's insulated correctly. So the next part here is going to be the impact, and there's really going to be no gradual onset. The leading edge of the Coriolis storm is going to be a very hard boundary. One moment you're going to have visibility 10, 12, 13 miles. Next, you can't even see your hand in front of your face. The sand wall's leading edge is going to be driven by that giant pressure differential, and it's going to hit as a physical force. You're going to have wind speeds at the leading edge of large haboobs on Earth that are over 100 kilometers an hour, and on an Arrakis scale, 700 or 800 kilometers an hour is probably pretty realistic. Inside the sand wall, or where the siege is, the sound of a haboob is going to be described as a roar, low frequency, overwhelming, and it's going to be felt as much as it's heard. And this matches real life, dust storm accounts almost exactly, because a lot of times dust storms, tornadoes, hurricanes, or really any high wind speed event is going to have a sound that's very similar to a freight train, and that's almost universal across all major weather events. It just sounds like a freight train coming at you because it's so loud and it's just so unyielding. So moving on to our next stage of our Coriolis storm, it's going to be inside the storm. And there's going to be three things that are happening simultaneously that each present a completely lethal hazard to an unprotected person. The first is going to be abrasion. Sand moving at several hundred kilometers an hour is basically sandblasting a person. If you've ever used a sandblaster before, you've seen how it takes rust off of metal. Just imagine what that would do to your actual skin. So things like a still suit are going to be completely needed because they're going to protect you. Secondly, is going to be your respiration. These tiny little pieces of sand are going to be getting inside your lungs, and it's going to make it so you can't breathe. So the still suits have, nose filters and, facial guards, basically, and that's going to address that exact hazard. The third is going to be disorientation. And, when you can't see your hand in front of your face, you have all this wind going around, knocking you off your feet. You're not going to know which way is up, which way is down, and you don't know how to get back to safety. So if you start walking in any direction, you're going to get lost, and you're probably going to not survive, unfortunately. Now, after all of that, you do have a moment of calm in the storm. Large Coriolis storms have a brief window of, relative calm near their organized center, which is kind of analogous to the eye of a hurricane. And this is physically consistent. Like any large, organized, rotating, low-pressure system is going to have, reduced wind speeds near the center of its pressure, in its low-pressure center, basically. And Fremen lore treat this zone as sacred and dangerous at the same time. Sacred because of the stillness, and dangerous because the trailing edge is often a little bit more intense than the leading edge. And that leads us to our final part of impact here, and that is the trailing edge. So the back wall of a Coriolis storm is going to hit harder and faster than the front. The pressure rebound, as the low pressure center passes overhead, creates a very sharp gradient on the trailing side. And then it's over, and Arrakis has totally changed. You have dunes that have moved, landmarks have shifted, paths that did exist before are just gone completely. And the entire desert has rearranged itself. And it's not metaphorical. The dune migration of several meters after a single major storm is documented in real life. So entire navigational references on Arrakis can be erased in a matter of hours, if not minutes. So their entire culture is going to be adapted to a landscape that can't be trusted to stay where you left it, which I think is really interesting from a world building point of view. The first step in avoiding a trap is knowing it exists. The Fremen survive Coriolis storms because of two things. They have knowledge accumulated over thousands of years, and they have technology evolved specifically for this environment. If you remove either one, their survival chances drop significantly. Just imagine a Harkonnen garrison soldier. He's equipped for enforcement and combat in a controlled urban environment. He's got heavy boots, he's got standard issue breathing apparatuses designed for chemical threats, and maybe some still suit water recycling technology in there too, but not as well as a still suit, like a true still suit. And he doesn't really have desert navigational training. He's going to be relying on his electronics. And in a Coriolis storm, what do you think this person's life expectancy is going to be? Is it going to be minutes, hours maybe, or is it going to be seconds? Because his breathing apparatus is probably going to clog up. He's not going to be able to see. His electronic navigational equipment is going to fail before the storm even hits. He's not going to know where he's at. So it's going to be very, very tough for someone who's untrained to survive in a storm like this. The still suit, on the other hand, is a really cool piece of technology. And it's driven by things that we use in the real world too. For certain, heat stress management systems, especially in desert environments, researchers have already proposed, like a moisture recycling garment that's very similar from a design standpoint to what a still suit So they're not like just purely science fiction. And the Fremen themselves are kind of like the other half of the equation. Like, the snowsuits are great, it's great technology, but like they have generations of adaptation to the desert, which means, like their mental response to heat stress, dehydration, and low oxygen is going to be completely different. And their cultural practices around water, where they treat it as, very sacred, not wasting a drop, or, they might spit as a sign of respect, is not superstition. It's a very, very strong behavioral expression of what the environment really does to a population over a long enough time. So the Fremen are most definitely optimized to, desert dwelling compared to anyone else, which is very obvious in the world of Dune. Without change, something sleeps inside us and seldom awakens. So here's the thing I want to leave you with, and I want you to sit with it for a second before we close out here. Everything that we talked about today, the thermal instability, the absence of moisture, the unbroken sand seas, and all the electricity going on in these storms, none of it's, all fiction, because it already exists. It's just 48 million miles away from where you're watching this right now, and that's on Mars. So Mars has a surface gravity roughly 38% of Earth's. It's got a very, very thin atmosphere. It's about 1% of what Earth has for pressure at the surface. It's got no liquid water, no vegetation, and it's got a surface covered in a very, very very fine iron oxide dust. And it experiences dust storms. And we're not talking about like little local ones. Like, these are global dust storms. In 2018, a dust storm initiated in the Perseverance Valley region of Mars, and within weeks it had encircled the entire planet, and the storm persisted for months. It reduced sunlight reaching the surface of the planet to the point where the Opportunity rover, NASA's cute little rover that had been on Mars for quite a while, could no longer charge its batteries. And on June 10th of 2018, Opportunity sent its last transmission. Now, the storm could be contributed to killing it, but it was getting old at that point too. So, just let that settle in. Like, a weather event on another planet had a big part to play in killing a piece of our technology from 48 million miles away. Now, let's compare the numbers. Mars's global dust storms reach heights of 40 to 60 kilometers vertically, which is insanely much more than what the 800-meter Coriolis storms on Arrakis talk about. And wind speeds during peak intensity has made it to be, between 100 to 160 kilometers an hour, which are lower than the ones for Arrakis, but they're consistent with what Mars's thin atmosphere can support. And the electrostatic charging in Martian dust storms is documented, and it's been studied. And once again, the changing of the surface has happened on Mars as well. Dunes are shifting and dust accumulates in other ways, which make the entire surface look completely different. The primary difference between Mars and Arrakis is the atmospheric density. Arrakis and Earth has a lot more of it, which allows the wind speeds that Frank Herbert describes. But the architecture of the storms, like the thermal engine, the feedback loop from the sand and the dust, the electrostatic character of these storms, and the way that the surface changes, it's all the same. It's the same storm. It's just Frank Herbert grabbed the dial and turned it up to 11. Now, Frank Herbert spent years researching before he wrote Dune. He studied, real desert ecosystems, real atmospheric science, and the Coriolis storm of Arrakis is not, a monster that he invented. It's a real phenomenon that he just scaled up and placed in a world where nothing was there to stop it. And it's kind of cool, that we live right next door to a real Arrakis, basically. We just haven't put a person on it yet. And when we do, You know, the first major dust storm season is going to teach us very quickly what the Fremen already know. And that's that the desert takes, and it does not like to negotiate. Well, that's going to be it for today's video. If you made it this far, thank you. This was a labor of love, and I hope that it gave you something new to think about. Whether you came here as like a Dune fan, just like me, if you like weather, just like me, or you're just someone who ended up on a weird corner of YouTube where fiction and science kind of overlap. Well, if you enjoyed the video, please subscribe. Please send a like. I got more of these planned. And I would love to hear your feedback and a comment on, if I should do more of these weather science videos on fictional worlds, or if I should focus on, real life weather, stuff going on in the US or Alaska or Hawaii. Just let me know. Drop a comment down below on that. So, take care, stay weather aware, and I will see you in the next one.